In lesson 12.2, we're going to talk about experimental probability of simple events. So the essential question is how do you find the experimental probability of a simple event? And then, of course, here's our standard that we're going to be working on, looking at the probability of a chance by collecting data and observing over the long run how something might occur. Of course, an experiment is something that you do to try to see what could happen. You do it in science all the time. You do the labs and the like. And we do some experiments here in math too. In this example, they're going to use a paper cup. You're going to toss it in the air and then see how it lands. And then, so what are the outcomes that, how could it land? It could land obviously sitting on the bottom, okay? It could land sitting on the top, or it could land where it's sitting on the side. So one of these outcomes are going to occur, and then you're going to do the experiment in class, and then you're going to answer these questions. So a couple of things we have to learn as far as how to calculate the experimental probability is some of the definitions. So you can use experimental probability to approximate the probability of an event. If you go back to 12.1, we're talking about the likelihood of that event occurring. An experimental probability is found by comparing the number of times the event occurs versus the total number of trials. So when there's only one outcome for an event, that's called a simple event. So here's our formula: the number of times an event occurs over the total number of trials. And if you remember, that's going to be the probability, okay, whatever that value that you come up with here. And you have to realize you'll never get greater than 1, or at least you shouldn't, because the number of times the events occurs cannot exceed the number of trials. So here in experiment 1, we have Martin has a bag of marbles. He removes one marble at random. He records the color, then puts it back in the bag. So the total stays the same. He repeats the process several times and records his results over here at the table. So the first thing you have to do is find out what's the total number of trials that you're going to have. So he took 12, 10, 15, and 13. He added those up. That's not how many marbles he has in there. That's the number of trials that he did. So keep that in mind. That's a little bit different there, okay? So he has 50 trials. And then what you do is, using the formula above, here he sets for the red marble, he had 12, so 12 over 50, and then he simplifies it. Does the same thing for the blue, 10 over 50, simplifies it to 1/5, and then so forth for green and in yellow. So right here, this in simplified form would be the experimental probability of picking a red, blue, green, or yellow marble. So here we're using a spinner on the your turn. 3 unequal sections, red, yellow, and blue. Table shows the results of when you're spinning around. Find the experimental probability of landing on each color. So the first thing we have to do is we have to total this up. So 6 and 14 is 20, plus 10 is 30. So that's our total. So now for red, we would have 10 out of 30. For yellow, we would have 14 out of 30. Blue, we would have 6 out of 30. And then, of course, you would simplify those to get down to a smaller ratio. So sometimes we use an experiment when it becomes very difficult or inconvenient to actually perform something. So we use this simulation to determine what our probability and make a prediction is going to be. So looking here at example 2 in this simulation, the baseball team has a batting average of .250 so far this season. This means that the player gets hits in 25% of their chances at bat. Use the simulation to predict the number of hits a team will have in their next 34 chances at bat. Okay, so they've summarized the information that we previously highlighted in the passage here. And we're going to use a standard deck of cards as our simulation to figure out how many hits that they could get in the next 34 chances. So what they do is they take, remember a deck of cards is 52. You'd shuffle them up, you'd randomly pick from them, and you record the results. And and then you put the card back into the deck. That's a very important thing because it changes your probabilities if you don't. And then you do that until you have 34 cards. So they have a scale here that tells us we're going to let H equal hearts, D equals diamonds, C equals clubs, and S equals spades. These are the 34 selections that they have picked out, and they're counting the hearts to represent their hits. So then we count. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the simulation is that 11 hearts is going to represent 11 hits in their next 34 chances at bat. The second way that we can go ahead and figure this out is that we can just say 34 hits, okay, and then they're going to a quarter of those, so we're going to multiply that by 1/4 are going to be what we're going to estimate out. So if we remember, okay, we do 34, and we're going to put that over 1 times 1/4. We multiply straight across, okay, so that gives us 34/4. For our fractions, remember the denominator is divided into the numerator, okay, so that's going to be 4 goes into 34. So 4 goes into 3, no. Does 4 goes into 34? Yes, it's 8 times because that's 32. We subtract, we have 2. We're going to put a 0 because we don't change our number. I bring it down. And 4 goes into 25 times. And that goes into it evenly. So we have a terminating decimal now. And it's going to be 8.5 hits. So the question is that out of 34 hits, they're going to, or 34 at-bats, they're going to hit a quarter of the time, which is 25%. And how many hits are they going to get? It's going to be 8 or 9 hits. Because remember, you're not going to get half a hit. So that's another way. That's more of a direct calculation than using a simulation. But I think this is the way that we would probably figure it out. So here's some guided practice for you to work on. And if you have any questions, let me know and I'll help you out. Thank you. Have a good day.